We're going to turn our attention now to section 4.8, the last section of chapter 4, which covers periodic properties. Now, periodic properties are properties of the representative family elements. Remember, that's families 1A through 8A that show a repeating pattern, properties that show a repeating pattern as you move across the period and as you move down the family. We're going to focus on three very important periodic properties here in this video segment. They are atomic size, ionization energy, and metallic character. Now, it's going to be important as we go through these that you really try to dig in and have it make sense to you. Otherwise, it's really easy to confuse whether something is increasing or decreasing as you move across a period left to right and down a family top to bottom. It's too hard to just memorize it, is what I'm saying. It gets confusing, easy to twist things around. Really try to anchor in understanding the principles, and then you can figure it out. So let's take a look at the first of the periodic properties, atomic size. And by atomic size, we're talking about the actual size of the atom or the radius of the atom, meaning the distance from the nucleus to where the valence energy level is located, the highest energy level holding electrons in it. And these are going to be incredibly tiny actual physical distances. What we're looking at here is changes in trends. Changes or trends, patterns, as you move across a period left to right or down a family. And in order to start this discussion, I want you to take a look at figure 4.17 in chapter 4. And when you turn to that figure, I want you to focus on the representative families. In other words, the S block and P block elements. They're shaded in yellow and green. Kind of remove the transition metals, the D block. Those families, by the way, are lettered with B letters, not A letters. So the properties that I'm talking about here apply to the A letter families, the representative families, 1A through 8A. You need to kind of excise the transition metals as you look at that figure mentally. And the pattern is really clear. Just kind of make a freeze frame in your head of what that figure is showing. And that helps you as you do the work required with this. Figure 4.17 is clearly showing that across a period left to right, starting on the left and moving to the right. And let's pull up this periodic table and illustrate. Starting to the left, moving to the right across a period, we see that atomic size is decreasing. Starting at the top of the family and moving down towards the bottom, we see the opposite. Atomic size is increasing. So let's see if we can't explain why that's happening so that we can understand and better anchor this pattern in our head. Across a period left to right, atomic size is decreasing. Now, this is not immediately intuitive. This is, in fact, the only one of the periodic properties that I kind of like to put I'm not sure I'm getting that. I'm not sure that's making sense to me. And let's illustrate. Here we look at period 2, lithium. It only has 3 protons, 4 neutrons in its nucleus, most isotopes of lithium, and 3 electrons. And you're saying that the pattern is that even though lithium has much fewer subatomic particles, it's bigger in size significantly than neon, which has 10 protons. Its most abundant isotope has 10 neutrons and 10 electrons. So way more subatomic particles in neon relative to lithium, but neon is smaller in size? That doesn't make sense. You'd think that more particles would mean bigger size. At least it doesn't make sense at an initial look or an initial glance. So how can we understand why, even though you are increasing number of subatomic particles within the atom, the size of the atom is getting smaller as you move across the period left to right? How does that make sense? Well, here's the explanation. Here's what puts it together. As you move across a period left to right, yes, you are increasing the number of protons in the nucleus. And what does that increasing number of protons do? It exerts a greater nuclear pull on the whole electron cloud. It pulls that entire electron cloud in closer. And even though you are also adding extra electrons, they're going into this exact same valence energy level as you go across a period left to right. They're not moving farther away. So electrons are filling the same valence energy level, but that increasing number of protons in the nucleus just pulls that entire electron cloud, including the valence energy level, closer to the nucleus. Therefore, atomic size decreases. So increasing number of protons in the nucleus exerts a greater attraction on the electron cloud and pulls that entire electron cloud in closer to the nucleus. Therefore, atomic size or radius decreases. Now, once that hurdle is met, then everything else, you just kind of reason your way through. Let's see if we can illustrate here. As you go down a family, top to bottom, atomic size is increasing. That is clearly shown on figure 4.17. So down a family, top to bottom, atomic size is increasing. And that is intuitive. That makes sense to us. We understand that every time we move down a block on the periodic table, we are starting a new energy level, adding an additional energy level as you move down a family of elements, and that new additional energy level becomes valence. So atomic size is increasing as you keep adding additional energy levels to an atom being filled with electrons. So down a family, top to bottom, atomic size increases. Adding an additional energy level as you move down the elements of a family, valence electrons farther from the nucleus, and atomic size is increasing. That's the first of the three periodic properties, and if we anchor ourselves in that, then we can reason our way through to understanding the remaining two. The second periodic property is something that you have not been introduced to before. It's called ionization energy. And ionization energy definition is the amount of energy required. It's required, meaning you have to put in energy, and we call that endothermic. Endo meaning in, therm meaning heat, meaning energy has to be inputted to the process in order for it to happen. So it is the amount of energy required to remove a valence electron from an atom. Valence electrons are always going to be farthest from the nucleus and most vulnerable to be removed or ionized. So ionization energy, the amount of energy required to remove a valence electron from an atom and convert the atom into a cation with a +1 charge. And let's illustrate ionization energy with this chemical equation. We're talking about a sodium atom. Notice nothing in the upper right-hand corner, meaning it's neutral, no charge. It's in the gaseous state. That's what the lowercase g subscript means. And you are inputting energy. You are giving energy to the sodium atom. It's called the ionization energy needed to strip an electron, remove an electron from that neutral sodium atom, now it has one more proton than electrons, and it is a +1 ion. This electron is removed. It can go several places, like to a nonmetal. We'll talk later about that. But it goes somewhere. It doesn't just disappear. Law of conservation of matter. That electron goes someplace, but it is removed from the sodium atom, and now sodium is a +1 cation. The reason that this process is endothermic, that energy is required, is because you need energy. It is required to pull the valence electron away from the attractive force of the nucleus. Nucleus is holding on to the electron. Therefore, you're going to have to input energy to overcome that attractive force of the nucleus and ionize the electron. What are the patterns that we see as we go across a period left to right? So first and foremost, across a period left to right, ionization energy values are increasing. So what does that mean? That means less energy is required to remove an electron from a lithium atom. And as you move across a period left to right, increasingly more energy is required to remove an electron from the remaining period 2 elements. So it takes more energy to remove an electron from neon than from fluorine. More energy to remove an electron from fluorine than oxygen. As you're going across a period left to right, ionization energy values are increasing. Now that is actually intuitive. It makes sense. Why? Because what did we say about atomic size as you go across a period left to right? Atomic size is decreasing. Electrons are being pulled closer to the nucleus. Atomic size decreasing as you go across the period. Therefore, it makes sense that you're going to need greater and greater amounts of energy to remove an electron from an atom and ionize it as you go across a period left to right. So, across a period left to right, ionization values are increasing. Atomic size is decreasing. Valence electrons are closer to the nucleus and harder to remove. More ionization energy is required. The exact same opposite reasoning is going to happen as you move down a family top to bottom. Ionization energy values are decreasing. So one more time, looking at the periodic table, as you go down a family top to bottom, it gets easier and easier to remove an electron from it, meaning less ionization energy is required. And that goes right back to atomic size. What's happening to atomic size as you go down a family top to bottom? Atomic size is getting bigger. Valence electrons farther away from the nucleus, experiencing less attractive pull from the nucleus, easier to remove them, less energy required to ionize that electron and take it away from the atom. So down a family, top to bottom, ionization values decrease. And rather than just simply trying to memorize that, reason it through. Atomic size is increasing. Valence electrons are farther from the nucleus, weaker attractive pull from the nucleus, and easier to remove. Therefore, less ionization energy is required. And that takes us now to the third and last of the three periodic properties that we're talking about now. There are additional ones, but these are the ones we want to introduce to you now. The third and last periodic property is metallic character. And when we use the term metallic character, we're talking about the degree to which an element displays properties like that of a metal. The more metallic an element is, the easier it is to lose electrons, right? The easier it loses electrons to form a cation. And that's the language of ionization energy. So we see that connection. The more metallic an element is, the easier it is to lose electrons. So, we're going to use, first of all, an important feature of the periodic table to help us remember this. Periodic table is going to give us this clue. Remember, there's a stair-step line. It's not showing well on this periodic table. Your periodic table will have it in bolder print. But that stair-step line separates nonmetals on the right from metals on the left. So the periodic table is telling us the answer. As you go across a period left to right, you're moving from more metallic character to less metallic character. Across a period left to right, metallic character is decreasing. Lithium is clearly a metal, but neon is absolutely a nonmetal. Likewise, periodic table is showing, using the carbon family as an example, that as you move down a family top to bottom, carbon is a nonmetal. It's shaded in blue, and to the right of the stair-step line, carbon a nonmetal, and as you go down its family and hit lead, we know that lead is clearly a metal. It's falling to the left of that stair-step line. So down a family, top to bottom, metallic character increases. So across a period left to right, metallic character decreases. We're mentioning that, and it's very easy to just track through and reason your way to why this is happening. Across a period left to right, atomic size is decreasing. Therefore, ionization energy values are increasing as you go across a period left to right. Size decreasing, electrons closer to the nucleus, more energy is required to ionize one, it's harder to lose electrons, and elements are less metallic going across a period left to right, increasingly less metallic. As you go down a family top to bottom, the opposite is happening. Metallic character is increasing. Why? Atomic size is increasing. Valence electrons farther away from the nucleus, easier to remove. Ionization energy is decreasing, easier to lose electrons, therefore resulting in more metallic character displayed by the elements. So putting that together, we can look at the table and reason that the most metallic of elements must be on the very left side of the periodic table and down at the bottom. Specifically, rubidium, strontium, cesium, and barium would be the most metallic elements, but they're not that common. So you often see sodium, magnesium, calcium, and potassium, or potassium and calcium. You often see this set of elements referred to as the most active metals. That's true based on abundance, but the most active are right down here in the lower left. The least metallic elements would be right up here in the upper right-hand corner of the periodic table.